All right, picking up with part 3 of the chapter 19 electrochemistry lecture, we left off talking about how to predict spontaneity of a redox reaction. So if we have a redox reaction with a positive cell potential, then that means that it's going to be a spontaneous reaction. And we can predict this just using table 19.1, which lists all these different redox reactions and the potential, the redox potential of all of those reactions. All right, so anything that is higher up on the table, these are things that are easily reduced. And as we go down the table, these are things that are less easily reduced. And the opposite of reduction is oxidation. So down here, these things are easily oxidized, and up here, these things are easily reduced. So anytime you pair a reduction reaction that's higher on this table than the oxidation reaction, that will happen spontaneously. So my sort of mnemonic here is that the cat is on top of the ox. Remember, the cat is reduction, the ox is oxidation. So if the reduction reaction is listed above the oxidation reaction on the table, then it will happen spontaneously, and it will have a positive E cell. But if the reduction reaction is lower on the table than the oxidation reaction it's paired with, it will be non-spontaneous, and it will have a negative E cell value. And that's because the ox cannot be on top of the cat. All right, so let's do some practice problems where we predict the spontaneous direction of a redox reaction. So we're given two metals, nickel and manganese, and it says write the redox reaction that occurs between nickel and manganese. Well, first we need to figure out which one is going to be oxidized and which one's going to be reduced. In other words, which one is higher up on that table 19.1. So if I go to table 19.1 and I'm scanning it, I'm looking for nickel and manganese. So I have found them both. I'm looking in the sort of products to find those two metals. So I see nickel is higher on the table. It's about 2/3 of the way down, and manganese is like 3/4 of the way down. All right, so since nickel is higher up, that means it's more reducible. All right, so the nickel is going to be reduced, and the manganese is going to be oxidized. So nickel is going to gain electrons, and manganese is going to lose electrons. So in this case, we'll have nickel is going from a positive charge. So it'll be the nickel reduction reaction on this page is nickel 2+ ion plus 2 electrons reacts to form nickel solid. And the manganese reaction, we're going to reverse it because it's going to be oxidized. So manganese solid is going to go to manganese ion plus 2 electrons. And if those are the two half reactions, we could add these together and say that the whole reaction is nickel 2+ plus manganese reacts to form nickel solid plus manganese ions. This is the reduction reaction because it's gaining electrons. This is the oxidation reaction because it's losing electrons, which means that if we made this into an electrochemical cell, like a voltaic cell, then the reduction is the cathode, this would be the cathode, and this would be the anode. An ox, red cat. Okay, so we could determine, if we had these two metals, nickel and manganese, which way the spontaneous reaction would go and determine that. So here's another form of the question, just asking which of the following reactions is spontaneous. So let's look at the first one. All right, so we've got to figure out which one's being reduced and which one's being oxidized. Or maybe let's do it this way. We have iron and magnesium. So let's look at the table. And iron 2 plus is higher on here than the magnesium 2 plus. So on table, that reduction potential table, iron is higher than magnesium. So in a spontaneous reaction, iron will be reduced and magnesium will be oxidized. So now we have to see if that's what's happening in this reaction. Iron and the magnesium there have 0 charges, 2 plus charge. So the iron's charge is going up. The iron here is being oxidized and the magnesium is the one being reduced. All right, so that is not this situation. So this is not spontaneous. All right, this reaction as it's written would not happen spontaneously. You would need to drive this reaction to happen using electricity. So the second one, let's look at that. All right, we've got iron and lead. So iron 2 plus and lead 2 plus. Lead is higher than iron on there. So I'll just write on the table, lead is higher than iron on the reduction potential table. So if the lead is being reduced and the iron is being oxidized, then this will be a spontaneous reaction. So let's see. Iron has a 0 charge, lead has a 0 charge, 2 plus, 2 plus. All right, in this case, the lead is going from 2 plus to 0, so the lead is being reduced, and the iron is being oxidized. And that's exactly the situation that would lead to a spontaneous reaction. So this is spontaneous. We could also solve this by calculating the cell potential using the number. So numerically we could do it, but we don't need to because we can just do it based on positioning on that table. But we would get the same result even if we solved it numerically. All right, so when a reaction is spontaneous and has a positive E cell, then those are the types of reactions that we can use to make electricity. Electrons will flow spontaneously, and we can capture those electrons, that electron flow, and use it to light things. So we call these spontaneous reactions, we can use them to make galvanic/voltaic cells, which we also just called batteries. And this is how batteries work. They actually contain a chemical reaction that is a spontaneous reaction that sends electrons out. Non-spontaneous reactions won't occur on their own, but we can make them occur by using electricity. And we call these electrolytic cells. All right, so these we need a battery for. So we can actually use the galvanic cell to run the electrolytic cell. And then we can use an electrolytic cell to recharge our battery. So electrolytic cells can be used to recharge batteries. And that's how rechargeable batteries work, essentially. If you recharge batteries, you plug them in. You put them into some kind of charger and you plug them in. You use electricity to recharge, to basically run the redox reaction in reverse so that you can reset your galvanic cell and make the battery work again. So a classic so we've spent a lot of time talking about these galvanic cells, these spontaneous reactions. Now let's look at an electrolytic cell. So a very classic one is the electrolysis of water, which is what you will do in the electrochemistry lab this week. So the electrolysis of water looks like this. If you have two water molecules and you apply electricity, it will break down into two molecules of hydrogen gas and one molecule of oxygen gas. And you can even measure this using, if you did this in two different sealed bottles with a balloon on top, you could watch those balloons inflate. And this is not a very well drawn to scale. All right, but this balloon here should be twice as big as the oxygen balloon because it should produce twice the amount of oxygen, because every 1 mole of oxygen, you're producing 2 moles of hydrogen. And notice that we have the solutions here, and we have an electrode on both sides. And we have wires connecting them, but the wires are connected to a battery because we actually need the battery to draw the electrons from one side to the other. So on the left side here, we have a reaction of water breaking down into oxygen and some hydrogen ions and some electrons. So electrons are on the product side. This side is lost, it's losing electrons, and that means that it's oxidation. So this is the anode side. And this side is gaining electrons. Here's electrons here on the reactant side. And reduction is gain of electrons. So that means that this is the cathode. All right. And electrons will always flow from the anode to the cathode. So they're going to flow here from these negative electrons are going to be attracted to this positive side of the battery, and they're going to leave from the negative side of the battery. Always the electrons will flow from anode to cathode, whether it's a voltaic cell or an electrolytic cell. Okay, so we were able to label this based on the half reactions, identify that this is a oxidation reaction because it involves loss of electrons. This is a reduction reaction because it involves gain of electrons. And we always know red cat and ox, so we can identify the anode and cathode. All right, so electrolysis of water is something that can be done to actually generate pure oxygen gas and pure hydrogen gas. So it's one of the ways that we actually can generate oxygen for use, like in an oxygen tank. It's also the reverse reaction of this, combining oxygen and hydrogen, or hydrogen and oxygen, to make water is very spontaneous and actually incredibly exothermic. It produces a lot of energy. And so this is the reaction that actually rocket ships use when they are taking off. They actually have two tanks, a tank of hydrogen and a tank of oxygen, and they both open up and they spontaneously react to form a whole lot of energy, which is where you get the flames and the heat and stuff, but also a lot of water, which is why you see all that sort of white smoke. It's not smoke, it's actually steam. It's all the water that's being produced as a product of this very exothermic reaction. There's also, they're also looking at using this system in cars to make sort of rocket-fueled cars, but it's a cleaner source of energy. And so if we can find a less violent way, a more controlled way to use it, then it's a really good source of energy. Okay, so another thing that electrolytic cells are used for, and by the way, in the lab this week, it's kind of, this electrolysis reaction kind of combines electrochemistry and acid-base chemistry, because what you're producing in this side is an acid, H+, and over here it becomes very basic because you're producing OH-. So you'll use an indicator to view the change in the pH at each of the electrodes, and you'll also be able to see gas bubbles forming. Oxygen gas bubbles forming on one side and hydrogen gas bubbles forming on the other side. And you'll see the bubble sizes are different. So that's kind of a cool observation to look forward to. Alrighty, another thing that we can use electrolysis for, besides making pure gases from water and making rocket fuel, is for metal plating. So a lot of jewelry, you take like a cheap metal and then you just plate it so it's not, you could have like earrings that are only sterling silver or gold on the outside. But most of the, the mass of the jewelry is actually something like nickel or zinc or something cheap. So you can make cheaper jewelry. You just cover the outside with a single layer of precious metal. And it looks just as nice, but it's not solid precious metal, so it's less expensive. Or we might do this with like silverware, etc. Nails might get plated, so you could take iron nails and plate them with zinc to make them less rustable, so they don't rust as easily. And so this is a process called metal plating. And money, of course, a lot of coins are coated this way. Like pennies are mostly zinc. There's only a thin layer of copper around the outside of the penny. So they're not pure copper. They're worth less than if they were actually pure copper. Okay, so in this case, we have an electrolytic cell. We have some silver. We have a silver electrode over here. And then we have some coin, let's say right here, that we want to plate with silver. And so we have our silver electrode and we have some solution with silver ions in it. And we run electrons so that the electrons are running this way. All right. And so that these ions, the silver ions, will end up accepting those electrons and forming solid silver on this coin and plating that coin, covering that coin in silver. So remember, wherever the reduction reaction is the cathode, and wherever the oxidation reaction is the anode. So the silver is losing electrons. Here are the electrons going to the battery. So the silver is losing electrons. We can see that the ion is silver 1+, so it just must be losing one electron. And at the cathode, we have some metal that's there, and what's happening is the silver ions from the solution are being reduced. So we've got silver ions. Reduction is gain of electrons, so it's gaining an electron and becoming silver solid on top of that metal. So it's a really common procedure that's used to plate different types of non-precious metals with things like silver or gold, precious metals. Okay, so let's do a practice problem. Consider the electrolytic cell below. We have 2 cells and we've got a battery. So we're told what the components are, but we need to label the anode and the cathode, and indicate the half reactions at each. So we need to figure out which one is going to be reduced and which one's going to be oxidized. So let's start with that. All right, so if we're given 2 metals and we want to know which one is reduced and which one is oxidized, we can simply look at our table 19.1, our reduction potential table. This is an electrolytic cell. So this is going to be a non-spontaneous. So we want the non-spontaneous situation. So the spontaneous situation, if I look at the table, I'm looking for nickel 2+ and cadmium 2+, and they're right next to each other. Nickel is higher than cadmium. So the spontaneous direction would be for nickel to be reduced and cadmium to be oxidized. But the non-spontaneous reaction is reversed, where the cadmium will be oxidized and the nickel will be reduced. So if that's the case, then nickel over here. So the half reactions would be nickel gaining electrons. So the nickel ion would gain electrons to form nickel solid. And on the cadmium side, that's the one that's going to be oxidized and losing. So cadmium solid becomes cadmium 2+ plus 2 electrons. This is an oxidation reaction. This is a reduction reaction. And we figured out which one was getting oxidized and reduced by looking at the table and figuring out that between those two metals, the non-spontaneous direction is cadmium being oxidized and nickel being reduced. Oxidation always occurs at the anode. So this side is the anode, and reduction always occurs at the cathode. So that makes this the cathode. Usually we put the anode on the left and the cathode on the right, but that's not always how you'll get it in a labeling problem. So you really have to determine which one is reduced and which one is oxidized. Okay, so we wrote the half reactions and we labeled the anode and cathode. Check. Now part B, indicate the direction of electron flow and label the battery terminals. Well, electrons always flow from anode to cathode. So anode is on the left, so that means that the electrons are going to flow this way. Right? Electrons will always flow towards positive charge and away from negative charge. So that's how you know to label the battery. The electrons will flow toward, the one that they're flowing towards is the positive, and they'll flow away from the negative charge. So we've labeled the battery. And then finally, what voltage is required to make this reaction go? Volts. How many volts? In other words, we need to know what is the E cell. It's asking us for the cell potential. So we actually need to solve that. So we've got these two half reactions. Nickel 2 plus 2 electrons. All right, this is the reduction reaction. So we'll get the reduction potential directly from the table. And the cadmium is being oxidized. So the oxidation potential is going to be the reverse. So I'll go ahead and put a negative sign there because we're going to flip the sign of whatever the reduction potential is for cadmium. So for nickel, if I look on here, it's negative 0.23. Negative 0.23. And for cadmium, it is negative 0.40. So we're going to make that positive 0.40 for the oxidation reaction. So the E cell is should I do this right? Negative 0.23 red cat frick. I did it backwards. I did it all backwards. Anybody catch that? Okay, so sorry, but looking at the table, all right, nickel is on top of cadmium. So if nickel is reduced and cadmium is oxidized, that would be spontaneous, not non-spontaneous. So I got this all reversed, and I'm not going to re-record this. We're just going to correct it. All right, so to be non-spontaneous, then the nickel needs to be oxidized and the cadmium needs to be reduced. And I found out that I made this mistake because when I got to the E cell down here, I was getting a positive value. And that shouldn't happen for an electrolytic cell. It should be a negative value. So knowing these things can help us catch our mistakes and correct them. So that means that the cadmium, well, we'll just erase all this. All right, means that the cadmium is the one being reduced. So here, cadmium 2 plus 2 electrons is forming cadmium solid, and the nickel is being oxidized. So the nickel is losing 2 electrons. All right, which means oxidation. This is the oxidation reaction. So this is the anode. This is the reduction reaction. So this is the cathode. Electrons will still flow from anode to cathode. So now it's going to flow this way since we determined that this is actually the anode. The electrons will flow to the positive side of the battery and away from the negative terminal of the battery. And now we can reverse these reactions as well. So nickel is the oxidation reaction. Nickel is being oxidized. And the oxidation of this will be negative, or the opposite, the inverse, whatever the opposite of negative 23 is positive 0.23. And for cadmium, cadmium is the one being reduced. It's gaining electrons. And we're going to just take that reduction potential straight off the table. It is negative 0.40. So the cell potential here is going to be negative now, negative 0.17 volts. So it's a very small amount of volts that are needed to run the cell, but we definitely expect this to be negative for an electrolytic cell. Should be non-spontaneous and have a negative E cell. All right, so this is the correct setup for it. Maybe I made that mistake on purpose to show you that it's okay to make mistakes and get things backwards. And eventually you'll hit a point where you figure out your error. If you're double checking, common sense checking, and recognizing that the energy to run to make this reaction go means that it should have a negative E cell. All right, and that's the last page of notes I have for you guys. So that's all we're doing in chapter 19 and a little bit of chapter 8. The end.